Okay, now we're recording. That's good. I'm almost fully recovered from my nasty cold over the weekend. So my voice is almost normal. And we are in chapter 19 still. Is that right? Did we finish? Yeah, we finished 19. But we do have questions from the homework, I'm sure, that we can answer for a little bit. I want to get on to chapter 20 before too long. So I will entertain 3 questions from the homework if you would like to ask them.
Does that mean each one of us get to pick a question? There's 3 of us.
Sure.
But since Packer's your son, he gets to see you all the time.
So he gets to ask 2?
Phil should go pick a third. Sorry.
Okay. I'm going to ask a bunch of questions later today.
I will be here most of the day if you want to come and ask questions. I may go over to UNL a little bit later, but I'll probably be here most of the day. So.
Super generator question keeps getting. Why did you have one with that?
Generator?
Yeah, not generator, the motor one. The one where you have a capacitor loaded with a certain amount of charge, and then it's
How the
Ah,
height?
yes.
I can't get the heights right.
I think
Okay. Well, let's.
Like I've done the trig, sine opposite over hypotenuse.
Well, let's figure out
Well,
what that problem is. Which problem is that?
it's second to last, I think.
This shouldn't count for the background.
I'm sorry. I just asked all the questions, and then none of them will count.
There you go. We got a system good here.
Number 9?
No, 11 or 12, I think.
Yeah.
Okay, so a capacitor is constructed. Now, one of the things that each of you is struggling with is this idea of setting up a problem. Now, I swear I've mentioned this at least 25 times, maybe 125 times.
Yeah, but you're going below the horizontal, right? I've tried.
Hold on a second, hold on a second. Cart before the horse. Wait a second.
You're the height.
You're the cart, I'm the horse. Let me speak first. Okay, so one of the problems that each of you is having is you've got calculatoritis. That you look at a problem and you write down a couple things and then you just start calculating. Button, 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 button. And then you get to the answer which is not the answer, and it's not even close to the answer, and it's nothing to do with the answer, and it's wrong, and you're frustrated. So let me go through again the thing that I always do when I do a problem. When I sit down with you and do problems, this is what I do on your papers. And when I do a problem in class, this is what I do. And I would recommend this is what you always do. And I don't just recommend it because I'm being that teacher that wants you to do something a specific way. Because I'm not going to grade you on how you do your homework. I'm grading you on whether or not you can get the answer. But I can almost guarantee you that if you've got 7 attempts and they're all wrong, that you didn't do this. Almost guaranteed. Because you're all smart enough, you all understand it well enough, but you're not doing this process. And this process doesn't have to be exact, but it's pretty important to do it. To do something like this every time you work on a problem, because it helps you to find your mistakes and it helps you to prevent your mistakes. Both. So here is the process. That's the wrong thing to put up. I always forget. Because that's going to be backwards on the screen again. I hate that. Okay, so let's fix this again one more time. Let's go to Zoom. Zoom, zoom, zoom.
Yeah, I think I did write everything.
There we go.
Yeah. I have a picture, I have all the formulas. Yeah.
Okay,
You got to do this.
So,
to get your PE. And then
what
you
is this
get your
problem
PE.
all about?
Converting,
It says we have a capacitor constructed of 2 metal rectangular plates right? And I'm going to start by drawing my capacitor. I've got my capacitor, 2 rectangular plates, okay? Dimensions 26 by 28, so I've got 26 centimeters by 28 centimeters. I'm going to label everything, place a plastic film between them, so you might want to draw a plastic film in between them. Like this, maybe. It has a dielectric constant of 2.5. Turns out that they tell you the dielectric strength too, but I don't care about dielectric strength because I'm just going to use the dielectric constant. Dielectric strength and dielectric constant are just two different ways of measuring the same thing.
Yeah, but the dielectric strength, doesn't it matter whenever you figure out your voltage? Because you think you got to take your E times your D distance of your thickness.
Your dielectric strength, you can use it, you're going to use it the same way you use the dielectric constant. The dielectric strength, we don't really talk about it in this class because it's just superfluous. But that dielectric strength is your dielectric constant times E naught, epsilon naught. So it's just another way of showing what the dielectric constant. So we're not going to mess with it. So I'm not going to do that. But anyway, the point is that I have a dielectric constant of 2.5, and then I have a 12-volt battery connected to this thing. So I'm going to connect a 12-volt battery. 12 volts, right? So I got a 12-volt battery on there, right? The charged capacitor is discharged to a motor. So we charge it up with a 12-volt battery, and then we discharge it once we've got it charged to a motor. So here's my motor. Connect to a shaft. It's going to lift something. Right? We discharge it to this motor, and that's going to do something. And it's going to lift this 48, we put it on the pulley or something, we'll lift a 48 gram, 41 gram weight. Okay? And we're assuming that it's 100% efficient. We want to know how high the weight will go. So I've got this chart of things that are happening, right? We want to know the height that it's going to go. So there's my chart. Now, the next thing I want to do, the next thing that some people would do is write down some of the formulas that I use, but I'm not going to do that next. Next, I'm going to finish my diagram by charting where the energy is going to and from. Okay? So I'm going to start with my capacity. I know it has to be energy because I have to do some work in the end, and doing work requires energy. So I know that it's energy that I'm going to be charting through this thing. So the first thing is I want to know the energy, which we use as U in the homework in the book. They call it PE, whatever you want to call it. But whatever you want to call it, U or PE, potential energy, we have some energy stored in the capacitor with these things. Now, with the things they've given us, with the dielectric constant and the area here, we should be able to figure out the capacitance, and we know the voltage. So we need some kind of energy thing that comes from capacitance and voltage. And then that energy is going to be discharged to the motor. And that potential energy, or whatever, is going to become work. And what is work? Well, work is equal to force times distance. Right? And what is the force? The force is going to be equal to the weight of that thing. And what is the distance? That's the thing we're measuring, which is the height. So I'm going to replace that with h, height. Now I can finish filling in formulas. Okay? Because I know where the energy is going, I know where it's coming from, I know where it's going to. I can finish filling formulas. Now there is a formula for the energy stored in the capacitor. If you use capacitance and voltage, it looks like potential energy stored in the capacitor is C times V over 2, I think.
CV squared.
Is it CV squared? CV squared over 2. That means I need to know the voltage, which I do know, and I need to know the capacitance, which I don't know yet, but I can calculate the capacitance, so let's write that down. Capacitance equals K times epsilon naught. times the area over the distance, right? The distance between the plates. And they did tell us the distance. What was the thickness of that plastic? It was
1 millimeter, which is 0.0, well, mine says 1 millimeter, 1, 2.
yeah. So mine says 1 millimeter.
1 meter.
So my distance, I know that distance. The thickness here, d equals 0.001 meter. And I've got to convert these ones here. This is 0.26 meters, and this is equal to 0.28 meters. When I convert those, right? And so I plug those things in, I calculate my capacitance, multiply by my voltage squared, divide by 2, get the potential energy. And then that potential energy goes to work. And then I solve for H. So in the end, I get potential energy from the capacitor equaling the work. So I get K epsilon naught A over D. All those numbers are given. Well, A is just length times width, right? Length times width. And we have the length and the width up there. And then that goes in, that's our capacitance. Our voltage is the V that they give us squared. We divide that whole thing by 2, put 2 right there. And then that has to equal the work that's being done, which is the force times the height. Now the height is the thing we're solving for, and the force we're going to divide on both sides, and the force is equal to mgh. Sorry, the force is equal to m times g. So that's the mass, which is 0.041 for the mass. No, that's not even right. Remember, let's just write that. There it is. So m times g, right there. And there's your answer.
Why would you make that big equation?
It's just a combination of all the other equations.
Well, it's easier to make it all
I understand
numbers.
that, but why would you do each step separately and go down the line?
Because this way I can see where I make my mistakes. If you just do each step separately and make a number every time, you can never find out where you made a calculation at. Because numbers are very difficult to track. Variables I can track. And this is the whole reason that I try to emphasize the importance of doing your math without your numbers first. Go through and do the math without numbers first, and then you can check. See, because now I can go back and I can say, look, I got this part right. Oh, wait, I made a mistake here. This D shouldn't be here. It should be somewhere else. I can go back and see where I made a mistake, and I can make a formula in the end where I can just plug in all my numbers at one time. It's way easier to plug in numbers one time than 10 times step by step.
See, but I have a harder time putting stuff into the calculator like that. Like you remember the last one where I had I had the whole problem right, but I didn't have my parentheses right. So it's harder for me to put it in the calculator like that.
Sometimes it can be. So in those cases, I'll do the steps now. So maybe I'll just calculate the numerator and then calculate the denominator and then divide. But you will make far fewer mistakes doing this than you will any other way, guaranteed. It's not something that I'm just saying to say, it's something I'm saying from hundreds of years of experience combined, my experience and other people's experience doing physics. It is just easier. And the reason is because I can go back and check my mistakes, I can check my work. If we do the calculations every step and we get a number every step that we carry, number, those numbers calculated together, we have no idea where the calculations came from when we go back and look at our work. This way I always know exactly where my calculations are going. I know exactly where the numbers came from. And this is extremely valuable, the methodology. Okay, if you can learn to do this all the way through like this, you will have much better success. I guarantee it. Okay? Some people just don't believe it. And some people will go through an entire physics class and never believe in it. And they tend to struggle. They tend to struggle with their homework more. But the people who believe this earlier on and learn it and practice it and understand how to do it by doing it and why it's so valuable tend to struggle less as the class goes on. Now this is why I mentioned this at the beginning of class and tried to emphasize it, because I really, really think that as the class goes on, the method of calculating step by step gets harder and harder and harder. It gets exponentially more difficult as the problems become more complex. Whereas this makes the problem, the problems are still harder, but solving them is really hard because it's still just the same old same. And that's the other reason that in your homework, I've been giving you homework problems where they ask you to give an answer that has no numbers in it. Right? Everybody asks me, why do you ask us to give you an answer with no numbers in it? You're just asking us to rearrange the equation. This is why. Because now I can plug in the numbers for anybody's answer. I can look at your homework problem, plug in the answers, and yours, and I can get the answer for anybody's problem because this is correct. No matter what numbers you have. Another advantage to using this.
When you map out the variables on those, you literally follow the energy flow like a single flow, where it's just
Yeah, I'm just following energy. Yep. Yep. And not only does this have problem-solving strategy usefulness, but it's practically useful as well. You two have worked in these fields where you have to track energy, where you have to track things through a system, right? Both of you have done that professionally, and you know the value of being able to track something. And so if you do that in your problem-solving strategy, not only tracking energy, but tracking variables, right? It's a very useful skill.
Yeah, but whenever I do it professionally, you start at one end and you work back step by step.
Yep.
You don't just go from the beginning to the end.
When you're doing it practically, in your work, for example, keeping track of things is not as important to you because you've done it 1,000 times. I can do this problem in one step because I've done it 1,000 times. But you guys have not. So it's not something you can do in one step. You could easily go to work and work on a problem with trains and not have to keep track of things.
It still doesn't change the fact that I cannot get the right answer.
Well, what are your numbers?
My numbers are 20 by 14
So you've got,
centimeters, which is,
so H equals, so your length and your width, right?
yeah,
Your length is 20 centimeters, so 0.02,
yeah.
and your width is 0.018, like that?
20 centimeters should be 0.2 meters.
No,
Yeah,
oh, it's 20, sorry.
0.2 and 0.14.
I was thinking millimeters, sorry. 0.2 and point what?
1.4.
1.4. And what's your K?
My K is 3.5.
3.5. And what's your mass?
My mass is 26 grams, which is 0.26
Okay,
grams.
and your D is 1 millimeter. So let's try it out here. We've got K is 3.5. Epsilon naught is 8.85 times 10 to the what? 9?
10 to the negative 12.
Oh, is it 8.85?
Yeah.
I keep getting this in. L is 0.2. Width is 0.14. Divided by M, which is 0.026. Divided by G, which is 9.8. Divided by 2, divided by D, which is 0.001, right? 1 millimeter. Okay. So, let's get a calculator out. If you want to do it by calculator, you can do it by hand if you want as well.
0.2 times 0.14.
Now what I'm going to do is I'm going to do all the numbers first. I'm going to leave off this 10 to the minus 12. A lot of people are struggling when they enter in the 10 to the somethings. So I'm going to do all the math first. I'm going to do the 3.5, I'll do the arithmetic. That's not scientific notation. We're doing 8.85, and we do a 0.2, and we do a 0.14. I'm going to put a times 10 to the minus 12 on the end number, and that's with later. And then 0.026, 9.8, 2, and 0.001. So all I've done is just rearrange the math so that the 10, rearrange that multiplication so that times 10 to the minus 12 is at the end. So I'll do 3.5, oops, not pi, 3.5 times 8.85 times 0.2 times 0.14 divided by 0.026 divided by 9.8 divided by 2 divided by 0.001 equals. So my overall number so far is 1701 times 10 to the minus 12. That's what I've got so far. Is that what you got?
No, mine was a simple, was a changing meters to centimeters to meters. That's the problem. That was the whole problem.
Oh, you didn't change it to meters?
No, I did, but I did it incorrectly.
Oh, I see. Well, this is the number that I've got as 1701 times 10 to the minus 12, and if I want to write this correctly in scientific notation, it needs to be 1.7 times 10 to the something, right? And so 10 to the minus 12 is something that, you know, moves your decimal point to the left, right, a bunch of times. So if I move my decimal point to the left a couple more times here, 3 times, and I have 1.701, then that takes 3 of these off. I essentially used up 3 of these, right? So this would be times 10 to the minus 9. Not 19, 10 to the minus 9. Not very much height. .7 nanometers. I wonder what the answer is here. Put in 9. Can I submit something here? Yeah.
That's the wrong. You're going online.
I know, I'm just trying to see if it'll give me the option to look at the answer. That doesn't let me look at the answer, right? Okay. Let's look at yours. You mind if I look at yours with the whole class in here?
Have at it, man.
Okay. What number was that?
12.
Let's see. 1, 2, 3, 4, 5, 6, 7. Yours is a 10 to the minus 7, and it's a different number.
That's for the maximum.
No, it's not. It's for this one.
That's for the height.
Oh, that's it.
Did we get all the numbers right? 3.5, 1 millimeter,
See,
26.
don't you have to use the 30 times 10 to the 6 voltmeters whenever you figure out your voltage? Whenever you put it into your CV? C voltage?
No, you don't have to use that.
See, I had 2.45 e to the 4th. I don't understand why it's above.
Well, it's
If I would have had,
well, you're off by a factor of, you know, a gazillion, but the
yeah,
number is close.
The
But
reason I had that is because I had 2.8 instead of 0.028.
yeah, that'll be part of it.
30.
That'll take up part of it, but not all of it.
Huh?
Let me look at the coding here really quick and see if they've got the same thing we do. So they've got potential energy, which is 1/2 CV squared. Oh wait, did we square our voltage? We did not. We forgot to put in the voltage squared. We have 1, 2, 3, 4, and then voltage squared. We forgot voltage squared. What's our voltage?
12, which would be 144.
Okay, so let me multiply by 144 real quick. Ah, now I got the right answer. Okay, so the real answer is this, actually. When you multiply this by 144, 12 squared, by 144, That's v squared, I forgot to put in the v squared here, right? So you multiply that by v squared, you get 245,076 times 10 to the minus 12. And that ends up being, to make this a proper scientific number, 1, 2, 3, 4, 5, it takes 5 numbers off there. That's 2.45 times 10 to the minus 7, which is the correct answer. Now, did you get a 2.4?
Yeah.
Okay, but yours was off by how much?
By the
Yours
by
was-
3 zeros, and that's because I had 2.8 instead of.
Was yours 2.4 times 10 to the minus 4? Was that your answer?
Yeah.
Okay, so yeah, yours was off by 3 zeros.
And that's because whenever I did my 2.2 times 0.14, I did it before and then tried to drop it down because it comes to 280.
Yep.
But wherever you,
So, and this actually illustrates exactly why I like to advocate for this, because when I'm doing this problem and I come up with an incorrect answer, I can check to see what I did wrong. And I went back and I looked and I said, what did I do wrong? I looked through here and I said, oh, I've only got 4 things multiplying together here. 1, 2, 3, 4. I had a 5th thing, v squared, that I forgot. And it was easy for me to see that because it was only one step back. And it was all variables, so I could tell what I was missing, right? Whereas if I just have a number each stage, if I go here and I've got this number and I look back at things because I calculated, I've got a number here, but I can't tell where the calculation is wrong, right? You can only tell if somebody else does the problem and you compare your answer to theirs, right? So if I do it this way, I don't have to have somebody else do the problem and compare to it. I can do the problem and go back and check my answer. So let's see, what time is it?
alright, so on the rest of that problem, right?
Yep.
What is the answers for this is obviously not very useful. Which of the following increases would help the weight go to a higher height?
Okay, so this is another place where this formula that I've written here becomes extremely useful. Without this formula, you cannot figure out what's going to make this go higher. Cannot do it. Okay? What's going to make this go higher? Things that make this number bigger. So if all the stuff in the top gets bigger, it gets bigger. If all the stuff in the bottom gets smaller, it gets bigger, right? And vice versa. If this stuff gets smaller, this gets smaller. If this stuff gets bigger, this
Alright,
gets
so what's a part of the top? Voltage?
On the top, we've got the first thing that we have. On the top is the dielectric constant. So if the dielectric constant increases, then H increases, right? If the length increases or the width increases, in other words, if the area increases, then this thing gets bigger. If the mass gets smaller, it can go higher. Is that an option?
No.
Okay. If the distance between the plates gets smaller,
No.
not an option. Okay.
So
Or then the last thing is the voltage, and if the voltage gets bigger,
so what's considered the dielectric strength then?
dielectric strength and dielectric constant are pretty much the same thing. If either of them get bigger, then because dielectric strength is just dielectric constant times E times epsilon naught. So either way, if any of these things in the top get bigger, then this height goes higher, right?
Alright, so what's the height max?
So the height max happens when you apply, when nothing in here changes except the things that are allowed to change in the problem. So the one thing that's you're allowed to change when you have a fixed capacitor, like you can't change the area of a capacitor without putting in a new capacitor. But you can change the voltage, right? So when you have a maximum voltage, well, what's the maximum voltage you can put on a capacitor? Well, essentially what that means really is what is the maximum capacitance of this capacitor, right? So what is the capacitance in general? The capacitance is K epsilon naught A over E. So it's this epsilon, this over E. That's your maximum, that's your capacitance, right? And you multiply that by the maximum voltage allowed on the capacitor. Well, what is that? And we can look in the book. It has the formula on some page. I don't remember where. Chapter 19, capacitors and dielectrics. Right here,
That's where that number comes in, the 30. 30 times 10 to the 6 voltmeter.
yeah, that is where it would come in.
So that's where you use that to figure out the voltage in the CV squared.
Yeah, that's where you use that to figure out what is the maximum capacitance. Yes, because right here, I thought they had an equation for this, but I guess they don't.
There's one there somewhere because I was trying to put it in for voltage.
This is the equation, but I thought they had it labeled. This is the equation right here, where it's just the definition of electric field is voltage. So it's electric field equals voltage divided by distance. The E is the strength, is the capacitive strength. So that E is that thing that has the volts per meter in it. And you plug in E, whatever your number is for volts per meter, and then the volts is the thing you're going to solve for, and divide by D, which is the 1 millimeter. So you do.
So you still have to put that into the other equation, though, right?
No, well, yeah. What you do is you calculate V from this equation, the maximum voltage you can put across it from this equation, and then what did they ask? I can't remember what the actual question is.
Height max, if the capacity was charged completely.
Okay, so yeah, then you plug that voltage back into this formula for V, and get the maximum height with that voltage. That's good.
Hey, go up to my choices. Alright, why is that wrong?
Which of the following increases would help the weight go to a higher height? It's not wrong. It's correct.
Why is the marks wrong?
Let's see here. Well, it's not marked wrong. It's the check mark says it's correct.
No, the green is correct.
That's funny. I think the one that they're saying is not going to change it is the dielectric strength, because the dielectric strength doesn't change.
I spent an hour on this problem.
That's not so bad. So that's not so bad.
No, just that part of this problem.
Just that part of the problem. The dielectric strength, so a good way of describing what the dielectric strength is, well, and they say in the book, it is the electric field at which the dielectric breaks down. It's where you get lightning striking through the dielectric.
So if it was increased, would it?
If that was increased, let's see.
That would be the dielectric constant also.
Right, which would mean it would get better.
Well, I have to agree with that, but I'm not sure what they're.
You're killing me.
Well, it's true. I do agree with it, but I'm not sure if saying that. It's like saying the dielectric strength of a particular material changes, but the dielectric strength of a material cannot change. So you'd have to literally change the material, but that's not what they're saying. So, yeah, but that's not what they're saying. So I'm wondering if they're being persnickety about it or
But
something.
then couldn't the dielectric constant not change either? Because
If
So
you can't
different
change the
materials
strength,
don't have a change.
Yeah, I don't know why they're saying that. So I don't, and I haven't even looked at the answer yet. So let's look at the answer here real quick. Let's see, how do I look at it here? Here we go. Let's see what it says for the choices area. Mass 0, which is voltage, 1 area of plates, and 3, which is dielectric constant. Yeah, they are saying that they don't like the dielectric strength as an answer. I don't know. I'd have to talk. I'd have to call them to see. I'll give you the points for that if you want. But I agree with you. Like I said, you guys get to be the guinea pigs this semester, and that's one that I'm not sure why they're justifying it one way and not the other way.
no, don't give me opposite, right? I would rather my answer on this paper agree with it if you're gonna give me this on the final. But whenever I study, I'll have to study the right thing, or what it thinks the right thing.
Yeah, I don't know why they're saying that that's not. Oh, I do know why. Let's see, do I? Let's see, electric field. I know, I don't know why, because I was thinking that they might have been thinking the electric field between them, because if the electric field in the capacitor increases, that actually decreases the capacitance, but they're not talking about electric field, they're talking about dielectric strength. And maybe that's what they were thinking, and then they confused themselves, because if they were just talking about the electric field between the plates increasing, then of course that is not true, because if the electric field between the plates increases, then that increases your possibility of arcing across the capacitor. So I think that's probably a mistake. I will look into it, because I can't really think of any justification for saying that that is not going to increase the energy there. But go ahead and answer it the other way and call it good.
So you're gonna call them and have them change it, or?
Well, yeah, I mean, but changing things takes time because you have to deliberate. It's not my question, so I can't change it. I have to find the person who wrote it, and then I have to deliberate with them whether or not it was a good question. And it's not always is the question incorrect. It may just be incorrectly stated. It may just be unclear what they were actually wanting. So fixing these kinds of things is not as straightforward as you might think. And because it is a user-driven community, you know, we have to kind of work together on things.
You can't just pop up and say you're wrong.
Yeah. You don't want to just throw it in their face. After all, they are doing a lot of work. And I've written some questions as well. All right, so does anybody else have another question? Hopefully not a 40-minute question.
One last question on this one, so that I understand this correctly.
Okay?
So whenever we do the pipe math, we take that E times E equals voltage divided by distance, and we use the max number.
Yeah, to get that last part, you're going to use the same formula right here, except when you plug in your V and square it, you're going to plug in your maximum V that you calculated from E equals V over D, where E is your dielectric strength. It's essentially the maximum electric field that your capacitor can handle, that your dielectric can handle without arcing, without getting some kind of short field. Charge leakage. Actually call it leakage current. All right. Now, moving on. Let's get out of Zoom here. And let's go to our book and move to chapter 20. The good news is that we're kind of stepping away from the theory part now. We're going to get into more practical stuff. And that's good news for most people because practical stuff tends to be a little bit easier to visualize than theory. You know, visualizing fields and potentials and all these other things, sometimes difficult. The downside to this is that there is still a fair amount of mathematics involved, particularly when we get into some of this later stuff with circuits. And so let's get started. Let's see what we can learn here. So we're going to talk about current, resistance, and Ohm's law. And we used water to teach this. Why? Because flow of water, flow of fluids, is very similar to flow of electricity in the way that we visualize it, in the way that we understand it. For example, you have this dam water here, and it's falling down this height from a high point to a low point, and in falling, it gains some velocity, right? With electricity, we have charges that go from a high point in potential to a low point in potential. They go from a high voltage to a low voltage. And in doing, they gain energy. We don't necessarily think of it as velocity necessarily, but it is a change in energy. They do gain energy as they go from that high point to that low point in potential. This is why you have a battery that has a positive and negative on it. The positive part shows you the high voltage. The negative part shows you the low voltage relative to the other voltage. And the flow of current goes from that high point, that positive, to that low point, negative, and it gains energy in doing so. And if you put something in between, that energy can be used. So if you put a light bulb in between, you can use the battery and that current going from that high voltage to that low voltage to light up the light bulb, or to run a motor, or to do something else. The problem with all of this idea, is Benjamin Franklin. Because when we're talking about charge flowing from high voltage to low voltage, we're talking about positive charge that flows. And guess what? It's not flowing. Positive charge does not flow. Negative charge does. So actually, the negative charge is going from the negative side of the battery to the positive side of the battery, but the current, as we define it, is going from the positive to the negative. So current is essentially the opposite flow of negative charge. Current is the opposite of negative charge flow. So if the current is going one direction, the charge is actually flowing the other direction. Thank you, Benjamin Franklin. Benjamin Franklin had a 50-50 chance of getting it right to choose which one moved, and he chose poorly, right? In this picture, you can see that the water has energy from this jumping water at the end, right? The water obviously has some velocity, it obviously has some energy because it jumps up and goes flying out here. In electricity, we know that it has energy because it does something, right? It lights up a light bulb, it moves a motor, it heats a heater, it does something, right? And usually while it's doing something, it's encountering some kind of resistance. It's flowing through something that has some resistance. So that's where the resistance is going to come. So here's our definition for electrical flow or electrical current. We call electric current I. I don't know why, but we do. And it's equal to the change in charge over the change in time. Okay, well, what does that mean? What that means is that we're going to have an amount of charge moving through an area in a particular amount of time. And we're going to use amps for our unit of charge. The ampere is named after another physicist, and it is equal to 1 coulomb per second. So if you have 1 coulomb of charge, now remember, an electron is 1 times 10 to the minus 16 coulombs of charge. So there's 10 to the 16 electrons in every amp of current going by every second. That's a lot of charges going by every second. It's a huge amount of charge. So 1 amp is a lot of current. And for those of you who have practical experience with electrical stuff, know that. You know that if there's 1 amp of current going through it, you better check the voltage before you go anywhere near it. Because it'll kill you in a quick hurry. It'll cook you. 1 amp of current, okay? If it's got any kind of voltage, any kind of energy in it, you do not want to be near it. If it's got no voltage in it, hardly any energy, it doesn't really matter. And that's really the difference between voltage and current. Current tells you how much charge is flowing. Voltage tells you how much energy it has.
1.6 times 10 to what?
Times 10 to the minus 19, that's how many coulombs of charge an electron has. And it's negative 1.6, right? So 1 amp is a lot of current. André Marie Ampère, one of the dead Frenchmen. So let's do a really quick, simple problem. We have a truck battery that moves 720 coulombs of charge in 4 seconds when you're starting your engine. How long does it take 1 coulomb of charge to flow through? Oh no, sorry. They want to know the current if you have 720 coulombs in 4 seconds. So what is the current in a battery, right? A car battery. And this is pretty typical for a truck battery rather, not a car battery. Car batteries don't do this much. So our delta Q is 720 coulombs. Our delta T is 4 seconds, 180 coulombs per second, which is 180 amps. So when a car is starting, it's got 180 amps cranking out, right? After it's started, it doesn't have nearly so much. But during its start, it has a lot. But what's the voltage in a car battery? 12 volts, which is not really enough to cause damage to a human being unless your hands are wet or the battery terminals are covered with acid, which can cause your hands to be wet. Okay? I'm sorry? Yeah, it can still, a 12 volts can still spark you if your hands are wet. But if your hands are dry, 12 volts is not usually damaging, but it can be because, what is a wet hand? Essentially, if your hands are sweaty, it can cause you damage. So you should never mess with a car battery, ever, with your bare hands or with uncovered terminals, ever. Because you just never really know. Because if you do have enough conductivity in your hands for that 12 volts to break through your skin, because essentially your skin's like a capacitor. Your skin has a dielectric constant to it, has a dielectric strength. And if that dielectric strength is less than 12 volts, because it's wet and your hands are clammy or it's humid outside or something like that, then that 12 amps can go through you. And that could be bad. It could be really bad. But if your fingers are drier, you have more and more dielectric strength in them, so less and less current will travel through you. It'll be very, very small in some cases, so you don't even feel it. But if you get 180 amps through you, good night. Another thing that you want to be careful of, when you're dealing with batteries or electricity in general, how many hands do you use? One. And which one do you use? Your right hand. Why?
Because it's not your heart hand.
That's right. Your left hand is your heart hand. If you use your left hand and you have a charge go through it, it's going to go right through the left side of your body, which is where your heart is, and it's going to go down to your foot, which is where your foot is grounded, and that charge is going to go through your heart, which is going to cause your heart to stop. Or it might even cook your heart if it's 180 amps. If your heart stops, it can start again. If you cook your heart, you might as well just put it on a plate and serve it, because it can't be restarted, right? If you put 2 hands on there, what's the problem? It goes going to go through your heart no matter what, because it's going to go straight across your chest, right? So you never use 2 hands, because you don't want it to go straight across, and you never use your left hand. People that are used to working with electricity will keep one hand in their pocket, their left hand in their pocket, and they'll work exclusively with their right hand, right? So you got to be very careful working with electricity. Second question says this large value current, Second one is, how long does it take 1 coulomb of charge to flow through a handheld calculator if you've got 0.3 milliamps current flowing? So milliamps, 10 to the minus 3. So this is 0.3 times 10 to the minus 3. So this is like 300 microamps. And we're going to do 0.3 milliamps current. So the 0.3 is the number that we plug in for our current. We rearrange this equation to solve for the time. And it takes 3.33 times 10 to the 3 seconds for that much current to flow through a calculator. Well, you would expect it to take a while. It takes about an hour. Because calculators don't use a lot of current. How do you know they don't use a lot of current?
Battery lasts forever.
Yeah, and it's got a tiny little battery, right? Current is all about flow of things. And if you want a lot of things to flow, you have to have a big source for them to flow, right? Your battery has to be big, your capacitor has to be big, whatever's providing that charge has to be big if you're going to have a lot of current flowing. Well, calculators don't have a big battery. It's pretty plain and simple. They can use little small, they can use just little tiny solar panels to flow and run off the lights in the room. It's really simple. So they don't have a lot of current. They would expect it to take a long time, even for a small amount of current, to flow. So here is a very simple circuit. Probably one of the simplest circuits that can be created. Probably the simplest circuit. We have a battery, which is your source of charge. Now, how does a battery create charge flow? It's a chemical process that creates a voltage difference from one side to another inside this chemical bath. You essentially got this acid bath inside with some electrodes on it, and this chemical process creates a positive potential on one side, a negative potential on the other. And then you have a potential, and the source of charge also comes from inside of the battery because of this acid creating this ion mixture. So anyway, the point being is that it creates a potential difference across the ends of the battery. And then you plug in what we call a resistor. A resistor is an object that resists the flow of charge. It slows down the flow of charge. The current wants to flow, but the resistor doesn't let it flow. And while it does that, it does work. The electrical flow or the current does work on the resistor as it tries to push through the resistor. But it's not the same kind of work that we're used to. It's not the kind of work that makes things move. Like work used to be force times distance. This is a different kind of work. This work usually makes things light up or heat up. Really both. So lighting something up or heating something up, which usually is the same thing, is a form of work as well. It's a different form of work, but it is a form of work. So in this case, we heat up this resistor, and the resistor is in the bulb of the headlamp, and it glows. So the energy gets lost. The voltage was the energy. That was the source of energy for these flowing charges. But that voltage gets lost. The energy gets lost. How does it get lost? It doesn't get destroyed, it just gets lost. But how does it get lost?
It changes to light and heat.
That's right. Light dissipates. Light goes out there in the universe and it just dissipates and gets less and less bright, and then it just kind of fades off, right? Heat does the same thing. It starts off hot and then it spreads out in the universe and just gets lost. So it gets lost into the universe. It's very difficult to recover because it just kind of spreads out forever. But it's useful. Helps us to see things, keeps us warm, things like this.
Super heat death universe.
I know, we hate that, but we'll talk about that later. Okay, so here they talk about the whole snafu that is Benjamin Franklin, where current is the flow of positive charge, but since positive charges don't usually flow, current is opposite the direction of the actual flow of charge. In a very simple circuit like this, it wouldn't even usually matter which direction we connected the bulb, because current, if it flows one way through a normal resistor or another way through a normal resistor, it doesn't really matter. It's still going to do the same thing. So you could flip the battery terminals on the headlamp, no problem. It would still work. In other situations, it does matter. In this one, it doesn't. just so that the charges are flowing. Here's a nice illustration of our problem with Benjamin Franklin. As current is flowing, if a current is flowing from left to right, that would suggest that positive charges are moving from left to right. But in reality, what's happening is that you have current flowing to the right, and when you have current flowing to the right, that means you have an electric field that is pointing to the right inside of the material. So when charges are moving, you actually get an electric field in the material. Remember, in the static electrical stuff, we never got electric fields inside of the materials. Electric field was always zero inside of a conductor. But when charges flow, there is an electric field inside, and that's actually what's pushing the electrons along, or pushing the positive charges along. In this case, though, in reality, when the current is flowing to the right, the electric field is to the right, but what's really happening is electrons are flowing to the left. But it's kind of like being in traffic when you're driving up to a stop sign and somebody else is going while you're stopping, and you feel like there's kind of a movement, vertigo going on. You know, you're not sure if you're going, stopping, moving, whatever. So really, it's your point of view. From the point of view of the positive charges, they are moving in the direction of the current because the electrons are all moving the other way. It feels like they're moving forward, right? So it's a point of view kind of thing. It still works. So we can't get too mad at Benjamin Franklin. So here's another example. We have a 0.3 milliamp current going through a calculator, and we want to know how many electrons are passing through this calculator each second. And we use this definition of current. The current equals delta Q over delta T, but now we're going to talk about the change in Q of the electrons. So we're going to actually put a negative sign on this, and this will change the answer for us a little bit. So this is how much current, charge is going through. The current of the electrons is the 0.3 milliamp current, and they're going to write it as a negative 0.3 milliamp current divided by the negative 1.6 times 10 to the minus 19 joules, and you get 1.88 times 10 to the 15 electrons per second. So it's still a huge number of electrons going through that calculator per second, even though it's a small current. 0.3 milliamps is 300 microamps, not very much current, right? I've been hit by microamps of current at 10,000 volts, and it hurts because voltage still hurts, but the current was nothing. It was just a little, you know, the current didn't cause me any damage, just the voltage hurt like a ball peen hammer hitting my hand. What is really interesting is that electrons do flow, but they don't flow very far. If you have a current flowing through a circuit, there is no single electron that will go all the way around the circuit. It just never happens. The electrons are not that free to move. They are free to move, but they're not free to just go forever. So what really happens is it's kind of like being in a room with a whole bunch of people lined up one after the other. And, well, you could do it with dominoes, it'd be even better and less cruel, I suppose. But then you just knock over the first person, and they knock over the next person, knock over the next person, and it's the domino effect, right? That's current. Current happens more like dominoes than like cars going down a highway. That's correct. Very much like the pendulum, the Newton's pendulum, the Newton's cradle or whatever, right? Yeah, it's very similar to that, where it's more, you know, you move for a short distance and then you kick somebody else and make them move, right? And then you stop or you bounce back or whatever you do. Actually, usually you stop and kind of. So the current kind of flows through this kind of domino effect thing. And while charges can go through a complete circuit, it takes them an extremely long time. And you have to have a pretty high voltage for that to happen. So it's this domino effect that causes it. They call this the drift current. So the drift current is it's a way of describing how these things move. And here's another way of seeing how this happens, because it doesn't just happen like dominoes either. The drift current actually happens as these things move forward, and then they'll hit something, and then they'll bounce off and move another direction. They don't move straight back and forth all the time either, because electrons are much smaller than the wires they move in. It's like moving in a huge room, much bigger than that, in fact. So they have this current that goes one way and then another way. The electrons actually bounce all kinds of different ways, but their overall velocity, if you average it over all the electrons over all the time, is forward. And we call that the drift velocity and the drift current of this thing.
It's forward, but it's against the flow.
Yeah, it is against the current is one direction, the electrons move the other direction, but the drift velocity is opposite the direction of the current. There's no doubt about that.
It's like a trout swimming upstream.
I'm really starting to get that.
It's more like a lake thinking that it's a stream because trout are swimming in one direction in the lake.
Get it?
If that makes any sense. It's like you're the lake and you're sitting there all nice and calm, and then for like 6 days, trout are all swimming in one direction. They just keep swimming in one direction through the lake, and all of a sudden you realize that you think that you're flowing in the other direction because the trout have all been swimming in the other direction. That's what current is like. Oh, anyway. Okay, so here is another way that we can think about current, and this is a more technical and scientific way. We have the change in charge, of course, over change in time, which is what we already talked about. But what is change in charge? What is this flow of, or movement of charge? This flow of charge is the number of charges that move through a particular cross-sectional area in the wire, right? But also, it's kind of more like how many of them you can trap in a particular section, volume of the wire, where you have a cross-section here and a cross-section here, per time. So how do we, in other words, what we're asking is, how do we calculate this change in charge? How do we figure out how many charges are moving through the wire at any given time? Well, the answer is that you take the number of charges, n, you multiply by the area that they're moving through, the cross-sectional area. Then you multiply by the distance that they have to move through, x. And then you multiply by the charge of each charge. And that will give you the total amount of charges passing through. But notice in all of this we have an x divided by t, delta t, where we have a change in distance over a change in time, which is the drift velocity. And that's what we wanted to get at here, is that the current can be defined as the number of charges moving through times the value of each charge times the cross-sectional area times the drift velocity. And this way, we can actually calculate the drift velocity of the charges, knowing the size of the wire. We know that the charges are electrons or protons, or however you want to think about it. And knowing how many charges are moving through, we can actually and the current, and we can calculate the drift velocity. So why not? Let's do it. So they tell us that we've got 12 gauge copper wire. What's the diameter of 12 gauge, you electricians out there?
2.053 millimeters.
Yeah, way to read the book. So the 12 gauge copper wire gauge, now gauge is, American wire gauge is a funky system, isn't it? So the higher you go in American wire gauge, the smaller it is. So 30 gauge is really tiny, whereas 8 gauge or 2 gauge, man, 2 gauge you have to have 8 people to carry it around. I mean, most of the stuff that people use is somewhere between 8 gauge and 30 gauge. But there are, applications for much bigger wires. I've used, I think the biggest I've ever used, the smallest gauge I've ever used is, I think 4. And that's a beast. But anyway. So anyway, 12 gauge copper wire is about, has a diameter of 2.053 millimeters. And if it's carrying a 20 amp current, then we should be able to figure this out. We know the diameter, so we should be able to figure out the area. You take the diameter divided by 2, square it, multiply by pi, you get the area. 20 amp current is our I. And they say that there's 1 free electron per copper atom. So that tells us the number of electrons that can move. Okay? Well, how does it tell us that? Well, they tell us the density of copper. So we're going to calculate how many copper atoms are in this wire per unit area, per unit length, and then we should be able to figure it out. So here's a solution. First of all, we're going to calculate the number. It's 1 electron per atom. There's the the number of atoms per mole, so there's 6.02 times 10 to the 23 atoms per mole. And then the molecular density of copper, we have 1 mole per 63.54 grams. So that's the molecular density, which they gave us up here. They gave it right here. They didn't give it to us. They gave us the regular density, and we convert it using the molecular weight up here on the periodic table. But that's the molecular density right there. And then you convert from grams to kilograms, because stuff on periodic tables are always given grams because of chemists. And then we multiply by our density here that they gave us. So we get this is our molecular density from the periodic table. Here's the density that they gave us. We multiply all that stuff together to get the number of electrons available for conducting current. Now it's different for different materials. Copper happens to be a very good conductor. We get a lot of electrons available per cubic meter with copper. Then we calculate the cross-sectional area, 10 pi r squared, so we take the diameter divided by 2 squared times pi, like I said. And then we plug the stuff in that we need to plug in. We're trying to calculate V drift velocity here. We rearrange the equation, plug in our numbers that we've got now, and we get negative 4.53 meters per second times 10 to the minus 4 meters per second. Notice that it's not that fast, right? It's not really all that fast. Drift velocity is 10 to the minus 4 meters per second, and the signals that it carries, in other words, the actual electricity moves closer to the speed of light. It's about 10 to the 8. It's not quite the speed of light, but it's pretty close. I don't know if they actually said that here. They didn't say it here in the problem, but it's true. In the discussion, they do mention it, that the signal that electricity carries is moving at about 10 to the 8 meters per second, which is close to the speed of light. Not quite the speed of light, but it's very close. And so that actually shows you that an object does not have to move at the same speed as the signal that it can carry, the signal that it can transmit. And this is wave mechanics. This is the same with sound. The air that carries sound never moves close to the speed of sound, but the pressure wave that moves through the air does move at the speed of sound, right? So waves are a phenomenal thing. They're really phenomenal. Of course, if you're moving at the speed of light, if you're a wave moving at the speed of light, you can't be moving in anything that has mass. It has to be moving through a vacuum. We'll learn more about that later this semester. So now that we understand a little bit about current, we need to move on to Ohm's law. So Ohm's law, named for Georg Simon Ohm, German physicist from not that long ago, a couple hundred years ago. He did a lot of experiments with circuits, a lot of experiments with electricity, and he was able to come up with a law that is called now Ohm's law. And it's a very simple equation. V equals IR, or voltage equals current times resistance. It's often written as I equals V over R. But Ohm's law works most of the time. So technically, it's not a real law. Physics laws are supposed to work all of the time. It was discovered later, not much later, but later, that as resistors heat up and as voltage sources heat up because of the flow of current, Ohm's law doesn't necessarily get obeyed the same way. And also that certain materials, in certain situations, like if the current increases more and more and more, and because of heat, Ohm's law isn't obeyed. And then also materials, as they get colder and colder and colder, start to not obey Ohm's law. It turned out to be a good thing that these things were discovered, because we were able to discover things like superconductivity, where Ohm's law, where that whole R thing in Ohm's law just kind of goes away. Where you can go down to a hospital and put a superconducting coil, connect a superconducting coil to a battery, and get a current going through this superconductor and disconnect the battery, and the current just lasts for 12 years, which I think is how long the current's been going in the MRI machine down at the hospital here. They started that current 12 years ago with a portable battery, well, actually a portable converter, but they started the current and then they disconnected the power source and sealed it up, and it's been going ever since. There's a current flowing around and around and around that circuit. And they have to keep it super cold. That's what all the noise is in the MRI room. It's the flow of liquid helium, which is always a very cold process, very loud process, rather.
So does that mean that eventually they'll be able to plug it back in?
Usually they don't have to unless they need to do maintenance on it. It takes a long time for that current to dissipate, if it ever does.
I thought you said it would be about 12 years.
12 years is what they've got going now, is how long it's been going now. And barring any real problems, it could go, I mean, theoretically it could go indefinitely. Nothing is perfect. So if they get any kind of cooling on it, or if they get flaws or imperfections in their superconductor, which can happen as well, then eventually it will decay. I don't know if it's decayed yet. Eventually it will. There's no avoiding it, but usually when it decays pretty rapidly, and then they just have to go in there and fix it and replace it.
I worked in coal mines in West Virginia, and we got this real big cable, right, and stuff like this. You know, it was like an extension cord, but it had a bunch of smaller cables in it for 1,000 volt,
Yep.
1,000 amps.
Yep.
Well, one of the other mines that we closed, we left a big roll up there, you know, and he told us, well, go get this roll, you know, because we had to replace the miner cable. We went up there, and we found this guy dead. Well,
You found somebody dead?
yeah. Well, what it was is he was going up there to take the copper and sell it, right?
Uh-huh.
And he went out there, and the coil sitting there in the sun had induced a charge in it. So whenever he went and touched it, it killed him.
So it actually wasn't the sun that induced a charge in it, believe it or not. What it was actually more likely the magnetic field of the Earth inducing a potential in it. And we'll learn about that not too long from now, but with the magnet, because I'm assuming it was a very long coil.
Oh yeah, it's like this big around and this high.
Right. So if it's a very, very long coil and it's coiled up in a loop, the magnetic field of the Earth that goes through it will create a potential across that coil. And then if you touch it, and if it's a very long coil and it has a lot of loops, that can be a huge potential, a huge voltage, and it can drive a lot of current. And that's probably what happened, is my guess. The sunlight would not necessarily have much to do with it. It could, because sunlight is a changing magnetic field, but it doesn't have a lot of magnetic field. The magnetic field of the Earth is much stronger. So the sunlight may have contributed to it as well, but I think the magnetic field of the Earth would have probably contributed more. So whoever coiled it up was not thinking,
No,
or just didn't know.
They left it on the roll.
Oh, it's just sitting on the roll. I see.
Yeah, on the new roll.
And usually a huge coil of copper like that will be grounded just for that reason. And somebody didn't know to ground it so that it wouldn't dissipate its current, its buildup. But yeah, I guess that's what you get for trying to steal, right? It would have been a big payday because that much copper is probably worth thousands and thousands of dollars, but probably more than that actually, probably hundreds of thousands. But anyway, yeah. So anyway, this is Ohm's law. So here's a very simple example. We have an automobile headlight, right? And we have 2.5 amps flowing when 12 volts is applied to it. We want to know what the resistance is of this headlight. And so we rearrange it to calculate for resistance, R equals V over I, plug in the 12 volts and the 2.5 amps, get 4.8 ohms, which is a pretty normal kind of resistance for a lamp. Lamps often have fairly low resistances because you want the current to flow through them. You want to get a lot of current flowing through them so they heat up and they glow. And low resistances for most things are in the ohm range. So 4 ohms, 10 ohms, 50 ohms, 100 ohms even are pretty low resistances. Once you start getting into thousands of ohms, we start to consider those normal kind of resistances in circuits. Thousands of ohms, kilo ohms, 100 kilo ohms, 50 kilo ohms. then you get up into the mega ohms, giga ohms range, and those are considered high resistances, things that don't allow a lot of current to flow. You have to put a pretty high voltage across them to get current to flow. In this case, 12 volts is enough, and particularly for an automobile because they only have 12 volts. So you have to have a pretty low resistance light for a current to flow. If you're doing light bulbs in your house, you can have a higher resistance because you have higher voltages, right? Okay, so we mentioned before that you lose voltage, you lose energy essentially when current goes through a resistance. And we can measure that loss in voltage or that drop in potential, which is analogous to the drop in energy or the change in energy by using what we call a voltmeter. When you connect a voltmeter to something, you want to connect it on either side of the element that you're trying to measure the voltage drop across. Okay, this is important. Voltmeters are used one way, ammeters, which measure current, are used another way. Voltmeters are almost impossible to break. You can pretty much hook them up to anything except a high power laser. I learned that one day in a laboratory where somebody was trying to measure voltage across a high power laser with a voltmeter, and I heard this big boom and a flash of light. And I looked around the corner, and this guy was standing there next to a smoking voltmeter that had been literally blown to pieces. It was not high enough resistance to handle that kind of voltage. And drove a current through it and just blew it to pieces. It's pretty funny.
So
The good thing was he wasn't holding the voltmeter. He had suspended it from the ceiling because he knew that might happen. But anyway, voltmeters are very difficult to destroy because they're very high resistance. They're usually way up in the like mega ohm resistance range. All they're trying to do is measure the energy difference from one end to the other of an element of a circuit. So you just touch on one side, touch on the other, and you're good to go. Ammeters that measure current are very easy to break. Remember this, because I almost always get somebody blowing one up in my labs in this class. Well, not blowing one up, it just burns out a fuse. But anyway, ammeters are not designed to check something on either side of an element. They're designed to replace a wire or replace an element in a circuit. So you actually put them into the circuit and let the current flow through the ammeter, and then it can measure the current. Current meters or ammeters have very low resistance. And so if you drive through too much current through them, you will heat them up and they will burn out a fuse usually. Most ammeters are built with fuses these days so that you can't hurt the meter, you just hurt the fuse.
So an ammeter has to be hooked up in series with a voltmeter.
That's correct, and we will learn more about that later. So, absolutely. When you have an ammeter and a voltmeter in one device, called a multimeter, you have a lot of things that you can do with that. It gives you a lot of options. For example, you can measure resistance. You can measure even capacitance. You can measure all kinds of things, but the downside is if you forget which one you're using and hook it up like it's a voltmeter, but it's actually working like an ammeter, then you're in trouble because you'll drive a lot of current through it and burn it out. So that's where the danger comes in. This one's kind of a cool little thing here. If I remember it's the right one. And go. Maybe? No? Doesn't like it, apparently. Let's try it again.
So,
Nope.
you have, like, say, these little tiny lithium 12-volt batteries versus a car battery. They both bring you 12 volts. Car batteries are 13. But can one be used, like, if you use them interchangeably, my mind tells me something going to explode.
Well, so batteries are designed for specific uses because usually of their startup or their cranking voltage for vehicles usually. So bigger batteries generally have a higher cranking voltage, or a higher cranking amps rather, not voltage. So they can provide more current to start something. If you put a bigger battery in a smaller car, it's not going to hurt the car. It'll just have more than it needs, and so it won't use it all.
So like our modems have our ONTs, they have a UPS that attaches to them, just a 12-volt battery.
Yeah, so what it is it's a 12-volt battery connected to a power supply. Well, I don't know exactly. It's probably direct current. You're probably using LEDs. So yeah, your UPC is just a direct current UPC. So it is just a battery connected to a power conditioner essentially, so that the power coming out is very clean. And then that drives your all your circuits, all your electronics, all your fiber optic stuff, all your light and everything else when the power goes down. Right? And that's all it is.
So if you had some type of freaking emergency, you didn't have one of those certain models, you'll only run off of those UPSs. So that 12-volt battery UPS is a solid battery with that. Could you theoretically run that off of car battery?
Yeah, as long as the power conditioner will handle that. Usually it'll handle any kind of 12 volts that can deliver the current it needs. So they'll usually put a sealed battery in there that's high quality so that they don't have to change it ever and worry about it.
At least they can swap them out.
So the only thing a power conditioner is pretty much a diode.
Yeah, pretty much. Okay, so that thing's not working, obviously. Resistance and resistivity. So, how do you determine the resistance of something? It has to do with its material, first of all, what it's made of. But it also has to do with how much of that material you're going through. And it's kind of like a pipe, back to our fluid analogy. If you have a tighter, smaller cross-section pipe, it's harder for water to flow through it, or anything to flow through it. If it's bigger around pipe, more things can flow through. Same thing with materials that are resistive, like wires are resistive. A wire that is bigger across will allow more electricity to flow through it more easily. So that cross-sectional area thing is an inverse relationship. So resistivity is equal to rho, the resistance is equal to the resistivity rho, which is the material it's made of, essentially. So every material has its own resistivity. Things that have less resistance, materials like copper that are really good conductors, silver that are good conductors, they have a low resistivity. They have a low number there. Things that are bad resistors like tungsten, stainless steel, not very good conductors. So their resistivity is high. Their resistance, the resistance of those materials is generally higher. But it's divided by the cross-sectional area because bigger area is better, smaller area is worse. You see that? Yeah. So a bigger area increases conductivity, which decreases resistivity. Smaller area increases resistivity. So it's an inverse relationship there. But the length of the wire also matters. How long you have to travel through it, right? And distance. And so if the length is longer, the resistance is higher. So this equation helps you to calculate the resistance of a particular material if you know its dimensions and what it's made of. Here's a table of resistivities. So I'm going to take a little bit of a break here, and I'm going to have you calculate, each of you. You're going to pick a material. Each of you pick a different material. And I want you to calculate the resistance of that material if it's got a 1 meter long wire made of that material and 1 millimeter in diameter. Go.
So 1.001. I'll send it
Pi r squared is the area of the circle. Cross section.
That is the reason.
All right, you guys got some numbers?
I think so. So wherever you gave us .001, that was the area, right?
You said it had radius of point, no,
A diameter of 1 millimeter,
a diameter. Okay, I did that one.
a diameter of 1 millimeter, a length of 1 meter, and choose your material. And put this on a separate piece of paper with your name on it. And it'll be a quiz. All right, so
Wait. That what you came up with?
Well, I was doing, material.
No, that's just for the rating, for your area.
Oh, for the area? I don't know what my area is.
the area should be 0.0005 squared.
Or times pi.
Or 0.001 divided by 2 squared times pi.
That's right.
That's the magnitude.
So it should be something like 8. Should have maybe it start with an 8. What's your number?
7.85
Oh,
e
pretty
to
close.
-7.
Sounds right. Okay, once you've got your resistance on paper with your name on it, you can go ahead and drop it in the
What's the symbol for resistance?
resistance is R,
Okay.
or you mean the units?
Units.
The units are the omega, capital Omega, which looks like an upside down U with tails on it, like this. Ohms. Right there. Go ahead and, just go ahead and drop it in the little drop box on the filing cabinet. And then we'll move on. So my guess is that our numbers are all going to be around point something ohms. Is that correct?
Mine was 1.2.
What material did you use?
Mercury.
Oh. Yeah, yours might have been wrong.
I use manganese.
Manganese?
Come out like 5.6.
5.6 or 0.56? Yeah, if you use one of these bigger ones, you'll probably be up around 1 ohm-ish for a meter of wire, I would guess.
I was tempted to use a resistor just so I could have a massive number. Sulfur. Hard rubber. Fused quartz.
Teflon is often used, right, for capacitors because it has this huge resistivity that increases its dielectric strength dramatically. It just does not allow current to flow.
Would fused quartz be better?
Yes, but fused quartz is very brittle, harder to work with in small,
So,
because you want it to be very small and thin.
Right.
Teflon is easy to make small and thin, you just stretch it. Fused quartz doesn't do that so well. I'm sorry? Oh, yeah. They can change. They do change. They always do. Okay, so let's go to calculating a resistor diameter from a headlight filament. We have a car headlight that's made of tungsten. Many light filaments are made of tungsten because they can handle the heat. You can be very, very, very hot, so hot that they're glowing, and yet still not break or melt. Not true of many metals. So that has a cold resistance of 0.350 ohms, and the filament is a cylinder that's 4 centimeters long, and we want to know what its diameter is. So we want to calculate the diameter from here. So what we're trying to do is isolate the area. If we isolate the area, then we should be able to figure out the diameter from there. So area equals resistivity times length over resistance. And we know the resistance is 0.35 ohms. We know the length is 4 centimeters. And we know the resistivity is that of tungsten. So we plug all those numbers in. And then once we've got the area, which they get here at 6.4 times 10 to the minus 9 meters squared, then they set the area equal to pi diameter squared divided by 4. Why is it divided by 4? Because it's radius squared, right? Yeah. So anyway, it works either way. So they go ahead and you could either solve for the radius and then figure out the diameter, or you could use this formula. And they do that. Once they've done that, they find out that the diameter is 9.0 times 10 to the minus 5th meters. Quite small. Which is really quite amazing. Tungsten is...
The reason they did it divided by 4 is because you're taking your square.
That's right. They squared the diameter
So
first.
if you take the diameter and divide it by 2 first, then you still square it.
It still becomes a divide by 4. That's right. So you can do it either way. This is just the way they did it. But what you find here is the diameter is really quite tiny. Less than 1/10 of a millimeter. Right? And yet that thing gets so hot that it glows and it still doesn't melt. Tungsten is quite an amazing metal. And that's why they can make, tools out of tungsten. They often make cutting tools out of tungsten. They even mix it with carbide every once in a while. Carbide is a form of carbon that's similar to diamond. If you have tungsten and carbide, you have a metal that is extremely hard, because tungsten's also a very, very hard metal, and very resistant to heat, doesn't change in heat, combined with carbide, which is very hard like a diamond. So you get a really great tool that can do a lot of things in high heat.
You can also use it for safety purposes. People can, say, getting their hand caught in some machinery and the ring stripping all the meat out of the bone. Because the ring will break instead of bang.
It's true. Or you just do what you're supposed to do and never ever wear rings around machinery.
I think if you were wearing a ring that's that hard and it broke the ring, your finger's not going to make it.
Well, so the story I heard when I was being trained as a machinist
Oh, I've seen it.
is on a lathe, somebody was wearing a wedding ring and it caught the chuck caught.
I've seen it.
Yeah, they caught the ring, ripped the finger and all those tendons
Oh,
all the way up to the elbow, right out. It just takes the whole thing with.
Yeah, the whole skin comes off, right?
Yep,
And
just
it's
pops
like
it off.
You got all your meat and some of your meat's hanging in the thing, and you can actually hold it.
And then you got a 2-foot long set of tendons.
And then you got your bones, your some whatever's left, and you got this over here, you got this here, and the rings over here. Yeah.
The crazy thing is if you get them to a hospital quick enough, they can reattach all that. They slit the arm all open and rebuild everything.
There's a specific type of injury. I can't remember what it's called, but I had some friends who like to screw with people.
Oh, we should probably stop recording this.
Yeah, I had another buddy that he lost these 3 fingers, right?
Yeah.
And I had to go out on them because it's 2 rollers that are like this big around, and they're like from here to the wall over there, and made out of solid metal to do involving with toilet paper, right? They spin really fast.
Yeah.
Well, they was feeding it in. Well, it sucked these 3 fingers in, and it squashed it flat. Well, I had to go in and peel
Off the machine.
because it took
Okay.
his skin and peeled it off.
Ah,
I had to peel that off the involving and give it to them.
Fun, industrial accidents.
good night. Okay, so enough of the grossness. The last thing I want to show you really quick is that the resistivity does change with temperature. And this is the equation that tells you, this row 0 here is the original resistivity, and This one is the new one when it changes temperature. So it's a very simple equation. You just have to know the change in temperature. Oh, you also have to know this alpha can be different for very large temperatures. So every metal has a different alpha as well.
There, listen to those.
Yep, right here. So each metal changes differently. You just plug in the numbers and you can get a new resistivity at different temperatures. And that's why Ohm's law is not truly a law, is because of that temperature change. But go ahead and get started on homework for this section, and we will see you guys tomorrow.
I need help.
And I will have office hours today too.
Huh?
I will have office hours today too.
Sadly, the only major industrial accident I've ever seen was a rail. And that was in Korea. This poor kid forgot his safety